Okay, so we've seen this before. That is, you want the joint to sweep a certain angle. So let's say that there's the initial starting point q0, there's an ending point qf, there's the initial time, there's the ending time. So you want to start here, you want to end here, and this is just one joint. Okay, and then you could have it for multiple joints. Now, if you want to track this, we've talked about trajectory generation. You could join it by straight line, but what happens with that is that the velocity is not continuous at the start. So what we did was, as a compromise, we said velocity should be 0 at the start and end, and that gave us this profile. Looks like a sigmoid. This is q dot f equals 0, and q dot 0 is 0. Okay, so we came up with the profile. This is going to be a reference profile. It's something like this: a0 plus a1t plus a2t squared plus a3t cube, where we computed a0, a1, a2, a3 by the conditions that initial speed, final speed is 0, initial position is known q0, final position is known qf. Now we can do this the same way as before. The dynamics would be mq double dot plus cq dot plus g equals tau. Nothing changes there. Control. Okay, how do we control the torque such that we get the joint to track this trajectory? Well, all you do is you still use the trajectory tracking, the control partitioning or feedback linearization controller. You just do it this way: q double dot ref minus kd q dot minus q dot ref minus kp q minus q ref. So this part, the changes which have taken place is that we have added the reference acceleration, we have added the reference velocity, and this part, the third part, is the same. And then we continue this with we add this more stuff, which I'm out of space, so I'll just write in the next line, plus g times q, or sorry, g, which is a function of q, plus c q q dot q dot. Okay, so why does this torque work? Okay, why did I even choose this particular torque profile? What we can do is to analyze this. Let's substitute so to answer the question, let's substitute 2, which is the torque equation, in 1. So we have mq double dot plus cq dot plus g equals, the torque is all this, q double dot ref minus kd q minus q dot minus q dot ref minus kp q minus q ref plus c q dot plus g. Okay, so we can actually cancel this c with this c, and cancel this g with this g, and then I'm going to just rearrange this thing. So let me just take it on the next page. Okay, so what we are left with is mq double dot equals mq double dot ref minus kd q dot minus q dot ref minus kp q minus q ref. So we'll move the right hand side to the left, and we'll end up with m q double dot minus q double dot ref plus kd q dot minus q dot ref plus kp q minus q ref equals 0. Since m is not equal to 0, the other term should be 0, which is this term should be 0. So q double dot minus q double dot ref plus kd q dot minus q dot ref plus kp q minus q ref is 0. If we take the E is basically the error between q and q ref, then we can write this as E double dot plus kd E dot plus kp E equals 0. Okay, but when you look at this equation, you'll see that it looks very similar to spring mass damper equation, right? Where E is replaced with X. So if it's a spring mass damper equation and we have total control over Kp, Kd, then we can actually control the system to be critically damped. So that's what I'm going to basically use this to show you how to do trajectory tracking on the pendulum next time. Trajectory for one pendulum. So here what I'm going to do is start the pendulum from 0, theta equals 0, get it to go to theta equals pi divided by 2. Okay, in some time t equals t1, or we can just put here t0, t equals t1. And then I'll get it back from theta equals pi divided by 2 to theta equals 0, from t equals t1 to t equals t2, where clearly you can specify what those times are going to be. And then for each of those curves, I would have something like this: theta ref equals a0 plus a1t plus same thing here. Maybe I should put a different constant. Let me just put different constants so it's not confusing. So theta ref, so that one, a10 plus a12 11 12 13t cube. So you can solve for those 4 constants as by imposing the conditions that you know what theta is at those 2 endpoints, but you also want it to start and end with 0 speed. So 4 constants, 4 conditions, you can solve for that. And then the second one would be a20 plus a21t plus t squared plus yes, again solve for the 3 constants or 4 constants, sorry, using 4 conditions. We write it like this. So it doesn't look like a square. Okay, so what's the equation? It's m q double dot plus q dot times q dot plus gq equals tau. More specifically, if you write the equation, it will look like this. This will be 0. There's no damping at the joint, so that term would be 0. Mg sine theta equals the torque So the controller which you would use is tau equals m q double dot ref. Then let me put theta double dot ref minus kp theta minus theta ref kd theta dot minus q dot plus gq. Well, obviously you substitute capital M as ml square. C would be 0 and G would be mgl sine. Yes, I'm going to show you for a this is a folder which I'll provide to you. It basically does this control for a single link pendulum. Then I'll also give you another file which does it for a double pendulum. With, of course, a different trajectory for the double pendulum. So this code is in this folder, which I'll provide to you for a pendulum trajectory tracking. It has two files. There's a one link traj and one link main. The traj basically generates the trajectory for you, while the one link main does the simulation for you. Here, what I show you is you can do the entire thing of symbolically generating the trajectory without writing a single line on paper. Here, there are two trajectories, so each of them have their own A's. The times are given here. The starting and end angles are given for the first one, for the second segment. Here I compute theta 1 dot, theta 2 dot, and so on. Everything is done symbolically. And then I also end up creating the equations symbolically. So 8 equations for 8 constants. And then you can see that I basically generate the A matrix, the B, and then the result of this is just the entire thing, which I'll get by, so it gives you the whole all the constants basically. Okay, those constants are copy pasted in here somewhere. They should be right here. All the constants are here. This part basically generates the trajectory. So you'll see theta, this is theta A is the first part, theta B is the second part. And so that's generated. And then see, the meat of this code is where I do the this is just generating the, I should call ODE somewhere. It's right here. This is the place where I call the ordinary differential equations to simulate the system. And this is one link RHS is my equations of motion. So that would call, that would be, this is animate control. Yeah, one link RHS. So this one basically writes the equations of motion, which is this. And then it has an input to it, the torque. Here I wrote torque as T1. That T1 comes from another file called control. And I would define the control here. So this is my feedback linearization. You can see it is theta dot ref, kp theta 1 minus theta ref, kd theta dot minus theta dot ref. Okay, so let's run this. It'll produce animation, goes up to 90 degrees and comes back. This is some of the plots. That was pretty fast. Let me run that again and also increase the pause. Let's make it 5. And then to make this animation slow, all you have to do is, so instead of 0, 2, let's make it 0, 5. So it'll go quite slow. Yes, it goes up and down. And then this is the plot. So you can see that the red matches the blue, which means that the tracking is perfect. And then the first one was the angle, second one was the velocity and position, and third one was torque. So what I did was I have another example, which I don't want to write down. This one simulates a two-link manipulator doing some kind of kicking motion. You can think of, when you have if you want to kick a ball, what kind of motion would you follow? So this is, I'm just going to play the main file. So goes back the second link, the green link, and then so this was generated by having two trajectories. For the top part of the leg, it was just going from minus 30 or minus 60 to plus 60, but for the bottom part, there were two trajectories. So this part of the code has quite a few things. Two-link EOM generates the equations of motion for you. They're very complex. It's difficult to generate by hand. That's why I have it there. This is the same file which was probably generated for the two-link manipulator we derived some time back. Just that the axes are different. Now the axis, the legs point down in the 0 configuration. Link 1 trash, link 2 trash are basically the files which generates the trajectory. In particular, let's look at link 2. Here we have, as the same thing as before, we have two trajectories because the green link, the bottom link, has to go backwards before it goes forward. So then we have something very similar. Here, however, I'm going from 0 to that's 0.5 plus minus 1.5. So it's minus 1, about minus 1 radian. It's going minus 1 radian back, and then it's going forward from minus 1 all the way to 0. So everything again is generated symbolically. Okay, so the output of this is copy pasted in the two-link main wherever I have the trajectory, and things go from there. This is more complex. I would say if you follow the one-link one, it's just fairly forward to take it to two links. Okay, one more thing, and we'll be done with this part of the course, feedback linearization. So far, we've seen trajectory tracking. That is, if you're given that the joint should follow a particular trajectory, what do? Many times, we're not interested in the joint angles. Well, we're interested in joint angles, but more interested in how the end effector moves. So we've seen how to create trajectories like, the figure 8, the lemniscate, or circle, and so on. So that particular trajectory was drawn in the task space. So this will be feedback linearization in the task space. Here's a manipulator, and you wanted to draw, let's say, a circle. This is, so for this particular trajectory, what you're given is x ref, y ref, right? You want the end effector. This is the tip of the second link, on which you might have attached a pen to follow a trajectory like, say, a circle. So this thing is called task space because doing things in that space, that is picking up objects, is typically is a task, and that is in the task space. This is in contrast to what we had earlier, which was called joint space. So this was trajectory tracking in joint space. Because here we're directly controlling the angles, versus here we're controlling the angles indirectly. We're first trying to get the angles. Well, we want end effector to follow something in Cartesian space, and then we use that information to figure out how do we control the joints. So this involves some flavor of inverse kinematics, which I will just do. Okay, so here x ref t, y ref t is given. Okay, and the question is, how to control the joints. Okay, so for feedback linearization, in joint space, which we've seen before, which was the previous section, we said that the torque should be m q double dot ref minus kp q minus q ref minus kd q dot minus q dot ref plus c q dot times q dot plus g of q. Okay, so that's the torque. Now, this can only be done, all these q's, everything here is joint space or theta for manipulator, right? But here we're given things in the task space or the Cartesian space. So the trick here is, well, if we can map the q's, x and y's in terms of q and q dots, then we are good. So what we'll do is we'll precisely do that. We can write x equals f of q, or let me write it in a different way. X ref y ref, let's call this capital X, is f of q. This, if you recollect, is also known as forward kinematics, right? Given the angles, you can figure out where the end effector is. So in order to solve for q, all we need to do is we need to do f inverse times x. This we have done quite a few times in this course, especially for the assignment where you try to get the manipulator, a two-link manipulator or a three-link manipulator to draw some curve. So that is the inverse kinematics. So let's call this our first equation, or rather, let me do it this way. This is q ref equals f inverse x ref. Let's call this equation 1. How do we solve this? Well, we've solved this using f obtained using f solve. So if you want to go back, this is what we did. It was homework 2 or something like that. Okay, so what we've achieved here is we figured out how to get q ref, right? You just invert f. F comes from forward kinematics. We also need q dot, and we need q double dots. How do we get that? So we can actually extend this idea to get the other things. So here is how we do it. We know that q equals f of q. This is the, sorry, capital X equals f of q. Okay, so what we can do is we can take the derivative of x with respect to time. That's tf tq times q dot. I use the chain rule. For tf dq is j, right? The Jacobian times q dot. So x dot ref is j times q dot ref. And so if you want to compute what q dot ref is, it's simply j inverse x dot ref, where capital X dot ref is small x dot ref y dot ref. This is number 2. It basically gives us a way to compute q dot, which again is needed in that equation, the feedback linearization equation. Okay, but we don't have to stop here. We also need q double dot. So I'm going to take the derivative of this term again. X double dot equals, so I have j q dot, and I need to compute the derivative of that. So I have to use essentially the chain rule. So I'll be j dot q dot. So I keep q dot constant. I take the derivative of j. Then I keep j constant. I take derivative of q. So I can put this as x double dot ref equals j dot q dot ref plus j q double dot ref. And so q double dot ref was x double j inverse. I'm just going to move things around and take the inverse of j. Minus okay, so this is giving us q double dot ref. Now we have everything we need in order to solve this. So we have now from 1, 2, 3, we have computed q dot ref, q ref, sorry, then q dot ref, then q double dot ref from capital X ref, capital X dot ref, x capital X double dot ref. And what remains to be done is to be used in this equation of feedback linearization. Q be q minus okay, so what happens here is we know this now because it comes from equation 3. We know q ref, which comes from equation 1, and q dot ref, which comes from equation 2. So I'm going to show you how this can be put together in controlling a manipulator, a two-link manipulator to draw. I think I chose it to be a Leibniz skate, which is the figure 8 or the infinity symbol. So the file I'll give you, you can check this is 5. Double pendulum Cartesian control. This is a Python code which does trajectory tracking in Cartesian space or the joint space. Sorry, in the task space. Okay, here's the last file. It has two parts to it. One is the equations of motion, which is the same as the one before. Here is the two-link main file. First, I'll run this. Let me decrease the speed. So let's make it 0.5. Okay, so the difference between this file and what you have seen before is that previously you just did not care about the dynamics. So you just put it in an environment there's no gravity. So if you make the manipulator draw the figure 8 in the horizontal space, then gravity doesn't act against it. But if you draw it in the vertical space, then gravity is going to hurt your capability to draw the figure 8 unless you compensate for the dynamics. So this file is probably slightly longer, it's 300 lines. A bunch of it is animation code, but the key thing here is that there is a profile which is the lemniscate curve, and that should be, trying to find it. Okay, this is the equation for a lemniscate. This is from that 50 curves. Okay, that's the equation. Sorry, x dot equals a cosine a tau tau. X equals x0 plus a times sine a tau is the equation. This is the equation, sorry. Okay, where tau is this thing. Okay, tau is a function of small t, which is time. And so what I did was to compute x dot, so which is derivative of this is sine, this cosine, a tau, tau dot, and the tau dot is basically the derivative of this. So now I did not compute this by hand. What I did was I put that in symbolic Python, and it just gave me what this is going to be. All this came from symbolics, which I don't have the code here, but should be very straightforward to do it. And then the same thing for x dot, y dot, and then there is a bunch of Jacobians which are needed, Jacobian dot which is needed. Again, those came from I believe I have all those things here. Yep, this code actually gives you the Jacobian, tells you how to compute the Jacobian. It also tells you how to compute Jacobian dot. So if you run this first, yeah, so this was taken and copy pasted in over here, and then the same for J. And then essentially there would be a similar to other files. There's something called control, which specifies the feedback linearization. Should be on top, I think. Let's go on top. Figure 8, end effector position, Jacobian end effector, two link trajectory, animate. Okay, here's the control. I need the mass matrix, CG, all that comes from the equations of motion file. This is the part which does feedback linearization, a single line, but it has theta dot ref, kp theta minus theta ref. So I would start over here and trace back how did I evaluate theta ref, and so on. It comes from the things I wrote in the notes, as well as from the functions here. So hopefully it's self-explanatory. Okay.